In this lesson, we want to learn how to find the greatest common factor, or the largest term, that's in a set of numbers or in a set of terms. To do that, we need to review what the word prime factor means. And a prime factor is simply a prime number. So what is a prime number? A prime number is a number that is only divisible by itself and 1. So if we look along the number line starting at 0, 0 is not divisible by itself. It is divisible by 1, so it doesn't meet that criteria. 1 is divisible by itself and 1, but that's kind of the same thing. So the first prime number that, when we're looking at prime factors, we want to consider is the number 2. Because 2 is divisible by itself, 2 divided by 2, as any number is, but it's also only divisible by 1. The next prime factor is 3, because 3 is divisible by itself and also by 1. If we look at the number 4, 4 is divisible by 4, and it's divisible by 1, but it's also divisible by 2, which is another prime factor. So 4, because it's divisible by something other than itself and 1, is not a prime factor. If we keep going, we think about the number 5. 5 has nothing else that can divide into it, so it is a prime factor. The number 6 is not a prime factor because it can be divided into groups of 2, groups of 3, groups of 1s, and groups of 6s. That's too many options. It's not only divisible by itself and by 1. Our next prime factor would be 7. 8, for a similar reason to 4 and 6, is not a prime factor because it's divisible by a lot of different things, or a lot of ways you can break it up into groupings. We might think that 9 is a prime factor, but it's not. It can be divided into 3 groups of 3, which is a criteria other than these two. And we could go on and on. Okay, so we get the idea of what a prime factor is. So our key prime factors are in fact these ones here that are single digit, because once we start getting up into other ones, they're unique, but they're possible, but these are the ones we're going to see the most. So let's find something called the greatest common factor for a set of numbers. So let's look at 12 and 8. Now, there's a couple of ways that we can show how 12 can be broken down into its prime factors and how 8 can be broken down into its prime factors. I'm going to do it using something called a factor tree. So I want you to think about what is a way that you could group 12 items. You can do 1 by 12, but you'll end up being in the same spot you are now. Maybe you do something like 2 groups of 6, or you could even do 6 groups of 2. 2 is a prime factor, so we can't break it down any further, but 6 can be broken down into 3 groups of 2. Okay? So now when we look at what's at the end here, we can see that 12 is equal to 2 times 2 times 3, or 2 times 3 times 2. You can put these in any order you want. I'm going to put them in increasing numerical order just because I want to make a comparison to the factors of 8 in a moment, and that makes the comparison easier. When we look at the number 8, we can divide it into 1 times 8, but again, that's not going to get us any further ahead here. How about we put it into 2 groups of 4? Okay. 2 is a prime factor. It can't be broken down any further, but 4 could be broken down into 2 groups of 2. And again, you'll notice that we're ending up here with prime factors that can't be broken any further. So we could rewrite the number 8 as being 2 times 2 times 2. Now, because I've set them up in this manner, I can make an easy comparison to see how many prime factors they have in common. So I notice that they both have 2 here as a prime factor, but they also have another 2 as a prime factor. Okay? So 12 can be thought of as being 4 times 3, and 8 can be thought of as 4 times 2. And when we put all of these prime factors together that they have in common, like we see in the red here, 4 is considered to be the greatest common factor, or GCF for short. It's the biggest number that divides into both 12 and 8. Let's try this again, and this time let's compare 3 different numbers. Let's compare 6, 8, and 24. So let's do a tree diagram for 6, let's do a tree diagram for 8, and a tree diagram for 24. So 6 can only be broken into 2 times 3. And both 2 and 3 are prime factors, so we finished breaking this one down into the prime factors that multiply to give it. We can do 8 again like we did in the previous slide. We can do 2 times 4, but 4 can be further broken down into 2 times 2. And so you notice that at the ends of all these trees, I have prime factors. 2 and 3 and 2 and 2 and 2. All prime factors that we see listed up here. When we look at 24, it doesn't matter where we start. We could start maybe by saying, let's see if 2 is a prime factor. And of course it is, because it's an even number. And we'd have 2 times 12. So there's one of the prime factors of 24. Could 12 be broken down further? Sure. Let's maybe try to use one of these to break it down so that we get to prime factors soon. We could use 2 or 3. It's even, so let's do 2 times 6. There's another prime factor. And then finally, we have 6, which can still be broken down. It's an even number, so it can be 2 times 3. And now we've reached prime factors of 24. So let's write those underneath here, comparing them. So 6 can be written as 2 times 3. 8 can be written as 2 times 2 times 2. And 24 can be written as 2 times 2 times 2 times 3. Okay, let's compare now and see how many prime factors 6, 8, and 24 have in common. Well, they all have a 2. And after that, the comparison stops. These two have a 3, but this one doesn't. And these two have a pair of 2's, but this one doesn't. And so we're looking for the greatest common factor for all 3 of them. So I can think of the number 6 as being 2 times 3. And I can think of the number 8 as being 2 times 4. And I can think of the number 24 as being 2 times the rest of this, which is 2 times 2 times 3. Well, these all multiplied together give me 12. And so therefore, I could say that the greatest common factor of 6, 8, and 24 is 2. Right there. Okay. Let's get away now from just looking at prime factorization of numbers, and let's see if we can do some prime factorization also of powers and of variables as well. I'm going to leave that up there so that we can refer to it in our further examples. So let's find the greatest common factor this time in 5 to the 3rd and 5 to the 6th. You might go, wow, I don't really want to draw a tree for that. Well, you really don't have to. Because when we think of 5 to the 3rd, 5 to the 3rd means 5 times 5 times 5. Exponents are just simply ways of showing repeated multiplication in a simplified fashion. Let's do the same thing for this one. 5 to the 6th means 5 times 5 times 5 times 3 more 5s. Well, now that we write it out like this, finding greatest common factor is pretty easy. We have a 5 here, we have a 5 here, and we have a 5 here. And so therefore, the GCF of these two numbers is 5 times 5 times 5, which I could write as 125, or I could just write it as 5 to the 3rd. And that would be an easier way to do it. Okay, let's try another example. Let's look at, instead of numbers with exponents, let's look at powers where we have a variable. Let's do x to the 4th and x to the 7th. Well, once we recognize what these exponents mean, that we know that this is x times x times x times x, and this is 7x's multiplied by each other. And now the comparison is easy. We can see that they have 4 x's as prime factors. And so therefore, the greatest common factor for x to the 4th and x to the 7th is x times x times x times x, or just simply x to the 4th. Let's try this again. Let's compare 3y squared and 9. So let's expand this out to see what it really means. 3y squared means 3 times y times y. And 9, we know, can be broken down into 3 times 3 as its prime factors. So now when we compare what is the greatest common factor for these two terms, we see that it's 3. Another way that we can think of this then is that 3y squared could be written as 3 times y squared, and this could be written as 3 times 3. See how I've just written the greatest common factor here first, and the leftovers immediately behind it, if you will. Everything's still being multiplied together. So therefore, the greatest common factor is 3 for these two terms. Let's try one more. Let's compare 21c squared d to the 4th and 28c cubed d to the 5th. While we're learning to identify greatest common factors, I think it helps for us to expand it out. Now you notice here we have two terms that we're comparing, and when we're looking at the GCF, we need to see numerically in the coefficient what is the GCF, and literally in this part of the term what is the GCF. Okay, so let's take 21 and let's recognize that its its prime factors are 3 and 7. So this means 3 times 7. C squared means times C, and d to the 4th means times d times d times d times d. And don't worry, you're going to get to a point where you don't have to do all this expansion, but I want you to see where the answer is coming from for now. 28 can be divided into 2 times 14. We know that 2 is a good prime factor to start with in a tree if you're not sure where to start, or if it's an odd number, maybe you can try 3 or 5, or 7, or the next one up here would be 11, of course. 14 can be divided into 2 times 7. So we know that 28 can be written as 2 times 2 times 7. So let's do that. 2 times 2 times 7. And then let's expand the literal part as well. C times C times C, and 5 D's. There we go. So let's look for numerical GCFs. The only one I see that they both share is a 7. When I look at the literal parts, I see that they share a couple of C terms and up to 4 D terms. Okay? So I want to rewrite each of these terms, putting their GCF out in front and then multiplying by the leftovers, if you will. Okay? So 24c squared d to the 4th could be written as 7 c squared d to the 4th times its leftovers. Its leftovers would be a 3, and that's it. And if we take a moment here to do distribution, we can see that 7 times 3 would be 24, and c squared d to the 4th times no other literal parts, or a value of 1, would be c squared d to the 4th. Let's do the same thing here with 28 c cubed d to the 5th. let's put the GCF out in front that it shares with 21c squared d to the fourth, which is 7c squared d to the fourth, and let's multiply it by the leftovers that we see here. Well, 2 times 2 is 4, and there's a c, and there's a d. And just to double check our work, we can check and see if the numerical coefficients multiply together give 28. They do. Does c to the first times another c, or c times c equal c cubed? Yes. And then d to the fourth times another d. Well, this is 4 d's being multiplied by each other, times another d would be 5 d's multiplied by each other. So there you have it. This is how to come up with the greatest common factor between a pair of or a number of different terms. In the next video, we'll look at identifying the GCF when it's a monomial, when it's a binomial, and we'll also learn how to factor by grouping it.